For most of human history, reality seemed straightforward. Space appeared vast and three-dimensional. Time flowed forward in a single direction, and matter felt solid and permanent. The universe looked like a giant container filled with stars, planets, galaxies, and life. We assumed that space was the stage on which reality played out, and that everything within it existed independently and objectively. However, modern physics has been steadily dismantling this comfortable picture, replacing it with something far stranger and far more unsettling. One of the most radical ideas to emerge from this scientific revolution is the possibility that the universe itself is not truly three-dimensional, but instead a kind of projection, a hologram. The idea sounds like science fiction, yet it originates not from philosophy or speculation, but from serious attempts to solve one of the deepest problems in physics. That problem begins with black holes. When black holes were first predicted by Einstein's theory of general relativity, they seemed to be cosmic dead ends, regions of space where matter collapses so completely that nothing can escape, not even light. According to classical physics, anything that fell into a black hole was lost forever. But when quantum mechanics entered the picture, this assumption created a paradox that shook the foundations of science. Quantum theory insists that information can never be destroyed. Every particle carries information about its state, its position, and its history, and this information must always be preserved. If black holes truly erase everything that falls into them, then one of the core laws of quantum physics would be violated. This contradiction became known as the black hole information paradox, and for decades, it resisted every attempt at resolution. The universe, it seemed, was breaking its own rules. The solution, when it finally began to take shape, was unexpected and deeply disturbing. Physicists realized that the information consumed by a black hole does not vanish into its interior. Instead, it is encoded on the black hole's surface, specifically on the event horizon, the invisible boundary beyond which nothing can return. Every particle, every quantum fluctuation, and every piece of information is stored on this two-dimensional surface, like data written on a cosmic screen. This discovery led to a profound realization. If all the information inside a black hole can be represented on its surface, then perhaps this is not a special property of black holes alone. Perhaps it is a fundamental feature of reality itself. In the 1990s, physicists Gerard T. Hooft and Leonard Susskind formalized this insight into what is now called the holographic principle. According to this principle, all the information contained within a region of space can be fully described by information encoded on its boundary. In other words, a three-dimensional volume of space may be equivalent to a two-dimensional surface that surrounds it. To understand how radical this idea is, consider a simple hologram. When you look at a holographic image, it appears three-dimensional, even though it is encoded on a flat surface. Remarkably, if you cut a hologram into pieces, each piece still contains the entire image, though with reduced detail. The information is not localized in one place. It is distributed across the surface. The holographic principle suggests that the universe works in a similar way. Everything we perceive as three-dimensional depth may be emerging from information stored on a distant, lower-dimensional boundary. If this is true, then space itself is not fundamental. It is not the basic fabric of reality, but an emergent phenomenon, similar to how temperature emerges from the motion of particles. We experience space as real because it is how our minds interpret the underlying information. Just as characters inside a video game experience landscapes and distances, without ever perceiving the code that generates them, we experience space without direct access to the deeper informational structure that creates it. This idea is not merely philosophical. In certain mathematical models, particularly in string theory, physicists have shown that a universe with gravity can be perfectly equivalent to a lower-dimensional universe without gravity. These two descriptions, though radically different, produce the same physical predictions. From the inside, there is no way to tell which description is more fundamental. Reality functions exactly the same either way. This equivalence strongly suggests that our three-dimensional universe could indeed be a projection of something more basic and lower dimensional. The implications are profound. If space is emergent rather than fundamental, then location itself is not a basic property of reality. Objects are not truly in space. Rather, space is how information appears to us when it is organized in a certain way. Your body, your brain, and even your sense of being located here may be the result of how information is structured and interpreted, not evidence of an underlying three-dimensional world. This perspective forces us to reconsider what matter actually is. At the deepest level, particles are not solid objects, but excitations of quantum fields. These fields, in turn, may be manifestations of underlying informational processes. In this view, information becomes more fundamental than matter or energy. Reality is not made of things, but of relationships, patterns, and encoded data. Once information takes center stage, an unsettling resemblance emerges between the universe and computation. This does not necessarily mean the universe was programmed by an external intelligence, but it does mean that reality behaves as though it is processing information. Physical laws act like algorithms, and the evolution of the universe resembles a vast computation unfolding over time. Space and time themselves may be outputs of this process, not its inputs. This leads directly to one of the most disturbing questions science has ever encountered. If reality is fundamentally information, then who or what is reading that information? In quantum mechanics, observation plays a critical role. Particles do not possess definite properties until they are measured. The universe appears to remain in a state of possibility until an observation forces a specific outcome. This has led some physicists to wonder whether consciousness plays a deeper role in shaping reality than previously assumed. If the universe is holographic, then reality may not be fully rendered at all times. Like a digital simulation optimizing its resources, the universe may only resolve details when they are observed or interacted with. From this perspective, consciousness is not merely a passive observer, but an active participant in the unfolding of reality. We're not just inside the universe. We may be part of the mechanism that brings it into being. The darker implication is that anything that is rendered can also be altered, compressed, or erased. If the universe has a finite informational capacity, then it is not infinite in the way we once imagined. Black holes, which represent the maximum storage of information in a given region, hint at hard limits to how much reality can contain. If those limits are ever reached, the consequences are unknown. At this stage, the holographic universe remains a theory, but it is one grounded in mathematics, physics, and experimental hints. It challenges our most basic assumptions about existence and forces us to confront the possibility that the world we experience is not the world as it truly is, but a projection of something deeper and more abstract. What we call reality may be closer to an image than to a substance. If space is not a fundamental feature of reality, then one of the most basic assumptions about existence begins to collapse. Every human experience is built around location. We live somewhere, move through space, and measure our lives in terms of distance and direction. Yet the holographic principle suggests that space is not the underlying container of reality, but a secondary effect, emerging from something deeper. This raises a disturbing and unavoidable question. If space itself is an illusion created by information, then where are you actually located? From the perspective of holographic physics, objects do not exist at specific points in space in the way we intuitively imagine. Instead, they exist as patterns of information. Location is not a fundamental property, but a convenient description that emerges when information is organized in certain ways. In the same way that a three-dimensional image appears on a flat holographic surface, your body and mind may be manifestations of information encoded elsewhere, projected into a form that feels spatially real from the inside. This idea becomes even more unsettling when applied to the human brain. For centuries, Neuroscience has assumed that consciousness is generated inside the skull, produced by electrical and chemical activity among neurons. While brain activity is clearly correlated with conscious experience, correlation is not the same as origin. In a holographic universe, the brain may function less like a generator of consciousness and more like a receiver or interface. It could be decoding information from the deeper structure of reality, translating it into thoughts, emotions, and perceptions. This perspective is controversial, but it addresses a problem that neuroscience has never fully solved: how subjective experience arises from physical matter. Known as the hard problem of consciousness, it asks how electrical signals and molecular interactions produce the vivid inner world of thoughts, feelings, and self-awareness. If consciousness is not produced locally but emerges from information encoded at a more fundamental level of reality, then the hard problem takes on a very different shape. Consciousness becomes a property of the universe itself, not merely a byproduct of biological complexity. The holographic framework also changes how we understand time. We experience time as a steady flow from past to future, but physics increasingly suggests that time may not be fundamental either. In holographic models, time can emerge from the way information is processed and updated. What we perceive as the passage of time may be the result of changes in informational states, not evidence of an underlying temporal river flowing through the universe. This interpretation helps explain why time behaves so strangely at the quantum level and near black holes, where it can slow down, stretch, or even appear to stop. If time is emergent, then it is not surprising that it can be distorted under extreme conditions. Just as a video can be paused, slowed, or rewound without altering the screen itself, the flow of time may be an effect of how reality is rendered, not a fundamental aspect of existence. Memory plays a critical role in this process. Our sense of a continuous self depends on our ability to remember the past. Without memory, the illusion of a persistent identity collapses. In a holographic universe, memory may not be stored entirely within the brain. Instead, it could be distributed across the informational structure of reality, much like a hologram stores the entire image across its surface. This raises the unsettling possibility that personal identity is not confined to the physical body, but is partially encoded in the deeper fabric of the universe. If identity is informational rather than purely physical, then death must be reconsidered as well. Traditionally, death is understood as the end of consciousness due to the failure of the brain. But if the brain is an interface rather than the source of consciousness, then death may represent a disconnection rather than a destruction. The informational patterns that define a person may not be erased when the biological system shuts down. Whether they persist, transform, or dissolve into the larger structure of reality remains an open question, but the holographic perspective prevents us from dismissing the possibility outright. This does not imply immortality in any simple or comforting sense. Information can be preserved without retaining individuality. A drop of water added to the ocean still exists, but it is no longer a drop. In a holographic universe, individuality may be a temporary configuration of information, sustained only while certain conditions are met. When those conditions change, the configuration dissolves, even though the information itself remains. The implications extend beyond personal identity to the nature of causality itself. If reality is encoded on a boundary and projected inward, then cause and effect may not operate in the straightforward, local way we assume. Events that appear distant in space could be closely related at the informational level. This may explain why quantum entanglement allows particles to share information instantaneously across vast distances. From a holographic perspective, they were never truly separate to begin with. Entanglement suggests that the universe is deeply interconnected, with separateness emerging only at the level of perception. Space creates the illusion of distance, but information ignores that illusion. In a holographic universe, the fundamental layer of reality is non-local. Everything is, in some sense, already connected. This interconnectedness has unsettling consequences for free will. If the universe evolves according to informational rules, and if every state follows logically from previous states, then the scope of genuine choice becomes unclear. Are decisions truly made by individuals, or are they the inevitable outcomes of informational processes unfolding at a deeper level? The holographic model does not eliminate free will, but forces us to question whether it exists in the way we intuitively believe. Despite these disturbing implications, the holographic universe is not a cold or meaningless place. If reality is built from information, then meaning arises from patterns, relationships, and experiences rather than from material permanence. Consciousness, perception, and understanding become central features of existence, not accidental byproducts. In this sense, the universe is not indifferent to observers. Observers are woven into its very structure. As we move deeper into this theory, a more unsettling possibility emerges. If space, time, identity, and even causality are emergent, then reality is far more flexible than we ever imagined. It can be reshaped under the right conditions. Black holes may not be anomalies, but windows into the underlying code of the universe. Places where the illusion of space breaks down and the informational structure becomes exposed. If the universe is a hologram, then it is not infinitely detailed. Every hologram has a resolution limit, a smallest unit beyond which finer detail cannot be represented. In traditional physics, this limit is often associated with the Planck scale, an unimaginably small length at which space and time themselves lose their conventional meaning. At this scale, distances can no longer be divided smoothly, and the familiar laws of physics begin to break down. From the holographic perspective, this may not be a failure of our theories, but evidence that reality has a finite informational resolution. The Planck length, roughly 10 to the minus 35 meters, represents the smallest meaningful unit of space that can be described using current physics. Attempting to probe beyond it leads to contradictions and infinities. In a holographic universe, this limit makes sense. Just as a digital image becomes pixelated when zoomed in too far, reality may reveal its underlying discreteness when examined at extreme scales. Space appears continuous only because we are viewing it from a distance. This idea is reinforced by black hole physics. Black holes represent the densest possible storage of information in the universe. There is a strict limit to how much information can be packed into a given region of space, and that limit is proportional not to the volume of the region, but to the area of its boundary. This result, known as the Bekenstein bound, aligns perfectly with the holographic principle. It suggests that the universe has a maximum information capacity and that reality cannot contain infinite detail. If the universe has a finite information budget, then it cannot store an unlimited amount of complexity. This raises an unsettling possibility. As the universe evolves, complexity increases. Stars form, galaxies collide, life emerges, and conscious beings begin to store memories and generate new information. If there is a limit to how much information the universe can hold, what happens when that limit is approached? One possibility is that the universe adapts by compressing information. In digital systems, compression reduces detail in areas that are not being observed or used. A similar process may occur in the universe. Regions of space that are not being measured or interacted with may not be fully rendered at maximum resolution. This idea resonates with certain interpretations of quantum mechanics, where particles do not have definite properties until they are observed. Reality may be economizing its resources. This leads to a disturbing thought. The universe you experience may not be fully real at all times. Instead, it may be conditionally real, with details emerging only when required by observation. From this perspective, observation is not merely a passive act. It is a process that brings aspects of reality into existence. Conscious beings may function as probes, forcing the universe to resolve its own informational structure. The idea of conditional reality challenges deeply held intuitions. We like to believe that the universe exists independently of us, fully formed and complete. Yet holographic physics suggests that completeness may be an illusion. The universe may exist as a set of potential states, with actualized reality emerging through interaction. In this sense, the universe is less like a static object and more like a process. The limits of resolution also affect our understanding of continuity and change. If reality is fundamentally discrete, then motion is not smooth at the deepest level. Objects do not glide continuously through space. They update their positions in tiny informational steps. Time, likewise, may advance in increments, like frames in a film. The illusion of smoothness arises because these increments are far too small to detect directly. This discretization has implications for determinism. If the universe evolves in discrete informational steps, then each step follows from the previous one according to specific rules. This makes the universe resemble a computational process unfolding according to an underlying algorithm. However, quantum mechanics introduces an element of unpredictability. Outcomes are not strictly determined, but governed by probabilities. In a holographic universe, this randomness may reflect limits on how information is encoded and accessed, rather than true indeterminism. Another unsettling implication concerns the stability of reality itself. Any system with finite information capacity is vulnerable to error. In digital systems, errors appear as glitches, noise, or corruption of data. If the universe is a hologram, then it too may be subject to informational imperfections. These imperfections could manifest as quantum fluctuations, anomalies in physical constants, or unexplained cosmic phenomena. While there is no evidence that reality is glitching in any obvious way, some physicists have speculated that certain unexplained observations could hint at deeper informational limits. The strange values of physical constants, the apparent fine-tuning of a universe for life, and the mysterious nature of dark energy and dark matter may all be symptoms of an underlying informational structure that we do not yet fully understand. The concept of maximum resolution also reshapes our understanding of infinity. In a holographic universe, true infinity may not exist in the physical sense. Space may appear infinite because it is continuously generated, but the underlying informational structure could be finite. This would mean that the universe is not an endless expanse, but a bounded system with strict limits, even if those limits lie far beyond our observational horizon. This possibility redefines the meaning of cosmic expansion. As the universe expands, it may not be creating new space in the traditional sense, but redistributing information. The boundary on which the universe is encoded may be growing, allowing more information to be stored and more complexity to emerge. Expansion, in this view, is not the stretching of space, but the evolution of the cosmic hologram. If this is correct, then the ultimate fate of the universe is tied to its informational limits. Traditional cosmology predicts scenarios such as heat death, in which the universe reaches maximum entropy and no further useful work can be done. In informational terms, this would correspond to a state in which the hologram can no longer generate meaningful structure. The projection would become uniform, featureless, and effectively dead. Yet there is another possibility. Information need not vanish for structure to disappear. Patterns can dissolve even while information remains conserved. In a holographic universe, the end of cosmic complexity may not mean the end of information, but the end of interpretable reality. The universe would still exist as data, but without observers or structures capable of decoding it, it would be indistinguishable from nothing. At this point, the holographic universe begins to resemble a philosophical puzzle as much as a physical theory. It forces us to confront the possibility that reality depends on interpretation, that existence without perception may be meaningless, and that the universe may only truly exist while it is being experienced. These ideas push the boundaries of science and philosophy, blurring the line between objective reality and subjective experience. The deeper scientists explore the foundations of reality, the harder it becomes to separate the universe from those who observe it. Classical physics treated observers as irrelevant. Planets moved, stars burned, and galaxies evolved whether anyone was watching or not. Observation was merely a way to record what was already happening. Modern physics has shattered this assumption. At the quantum level, observation is no longer passive. It is participatory. The act of measurement changes the outcome, forcing the universe to choose between possibilities. In quantum mechanics, particles exist in a superposition of states until they are observed. Only when a measurement is made does the particle settle into a definite position or property. This phenomenon, known as wave function collapse, has no clear physical mechanism. The equations of quantum theory describe smooth, continuous evolution, yet observation introduces sudden, discontinuous change. The universe behaves as if it is waiting for something to happen before deciding what is real. Within the framework of a holographic universe, this strange behavior begins to make sense. If reality is encoded as information on a lower dimensional boundary, then what we perceive as physical events may be the result of information being accessed, decoded, or updated. Observation becomes a process by which certain informational states are selected and rendered into experience. In this view, the universe does not fully exist as a concrete structure at all times, but as a set of potential realities that crystallize through interaction. This raises a difficult question. What qualifies as an observer? Is it any interaction between physical systems, or does it require consciousness? Some interpretations of quantum mechanics argue that consciousness plays no special role, that measurement can occur without awareness. Others suggest that conscious observation is fundamentally different, introducing an element that cannot be reduced to physical processes alone. The holographic principle does not settle this debate, but it reframes it in a new and unsettling way. If consciousness is itself an informational phenomenon, then it may be deeply woven into the fabric of the universe. Rather than emerging late in cosmic history as a byproduct of biological evolution, consciousness could be a fundamental aspect of reality, present wherever information is processed in sufficiently complex ways. In this sense, human awareness would not be an anomaly, but a localized expression of a universal property. This idea aligns with a philosophical position known as panpsychism, which proposes that consciousness, or at least the potential for consciousness, is a basic feature of all matter. While panpsychism was long dismissed as unscientific, modern physics has reopened the door to such possibilities. If reality is fundamentally informational, then the distinction between matter and mind becomes less clear. Both may be manifestations of the same underlying structure. The holographic universe also suggests that observers are not separate from the cosmos, but part of its internal self-description. When the universe observes itself through conscious beings, it may be increasing the richness of its own informational patterns. In this sense, observation is not merely a process happening within the universe. It is something the universe does to itself. This perspective gives new meaning to the idea that the universe is self-aware, not in the sense of a single, centralized consciousness, but as a distributed process of awareness emerging wherever information becomes sufficiently complex and self-referential. Each conscious being becomes a node in this cosmic network, a point where the universe reflects upon its own existence. The unsettling implication is that meaning may not exist independently of observers. Without observation, the universe may still exist as information, but it would lack interpretation. It would be data without context, structure without significance. Consciousness, in this view, is what transforms raw information into experienced reality. This idea also reshapes our understanding of purpose. Traditional science avoids questions of purpose, focusing instead on mechanisms and causes. Yet if observers play an active role in shaping reality, then the emergence of consciousness may not be an accident. It may be a necessary feature of a universe capable of generating stable, interpretable structures. A universe without observers would be incomplete in a fundamental sense. The holographic model also casts new light on the anthropic principle, the observation that the laws of the universe appear finely tuned for the existence of life. Rather than being a coincidence or the result of multiple universes, this fine-tuning may reflect the requirement that the universe be compatible with observation. Only realities capable of supporting observers can become fully realized. This does not imply that the universe was designed with humans in mind. Instead, it suggests that observers and reality co-evolve. As the universe develops complexity, it generates observers, and those observers, in turn, participate in defining what the universe becomes. Reality is not a fixed object, but a dynamic relationship between information and awareness. There is, however, a darker interpretation. If reality depends on observation, then the disappearance of observers would have profound consequences. A universe without consciousness might continue as raw information, but it would no longer be a universe in any meaningful sense. It would be a silent structure, devoid of experience, interpretation, or meaning. In this view, consciousness is not just a feature of reality. It is a condition for reality as we understand it. This perspective forces us to reconsider the ultimate fate of the cosmos. If intelligent life is rare or short-lived, then the window during which the universe is fully realized may be brief. The vast stretches of cosmic time before life emerged and after it disappears may represent long periods in which reality exists only in a latent, uninterpreted form. At this stage, the holographic universe confronts us with an unsettling choice. Either consciousness is a fundamental feature of reality, deeply embedded in the universe's informational structure, or reality itself is incomplete without observers. In both cases, the traditional separation between mind and cosmos dissolves. We are not detached spectators watching the universe from the outside. We are part of the mechanism through which the universe exists. When people imagine the end of the universe, they usually picture a dramatic physical event, a catastrophic collapse, a fiery destruction, or a silent freezing of all matter into darkness. These scenarios dominate cosmology because they are rooted in classical ideas of space, time, and matter. But if the universe is holographic, then its true ending may not be physical at all. It may be informational. Reality could end not with an explosion or a collapse, but with a gradual loss of meaning. In a holographic universe, existence depends on information being structured, processed, and interpreted. Matter and energy are not fundamental substances, but expressions of underlying informational patterns. Space and time emerge from how those patterns are organized. Consciousness, in turn, is what gives those patterns coherence and significance. If any part of this chain breaks down, the universe as we experience it begins to unravel. One possible end is informational saturation. If the universe has a finite capacity to store information, as suggested by black hole physics, then there may come a point where no new meaningful structures can be formed. Complexity would stop increasing. Stars would burn out, galaxies would drift apart, and eventually no new observers would emerge. The universe would still exist as data, but it would no longer be capable of producing experiences. It would be a completed computation with no further output. Another possibility is informational erosion. Over immense spans of time, the fine details that allow reality to be interpreted may be lost. This is not the destruction of information, which physics forbids, but the loss of structure. Patterns dissolve into noise. Distinctions blur. The holographic projection becomes increasingly uniform until there is nothing left to distinguish one region of reality from another. At that point, the universe would still technically exist, but it would be indistinguishable from nothing. This scenario reframes the concept of cosmic death. The universe does not need to disappear for reality to end. It only needs to lose the capacity for interpretation. Without observers, or without structures capable of supporting observation, the universe becomes a silent archive. All information remains preserved, but none of it is ever accessed. Reality becomes unread data. This idea casts human existence in a stark new light. Conscious beings may represent rare moments when the universe becomes aware of itself. Our thoughts, perceptions, and questions are not insignificant side effects of chemistry, but instances of the cosmos reflecting on its own structure. In a holographic universe, meaning does not exist independently of experience. It arises when information is interpreted by consciousness. This does not grant humans a privileged position at the center of the universe, but it does give observation a profound role. Any conscious system, anywhere in the cosmos, participates in sustaining reality as an experience phenomenon. Life, intelligence, and awareness become cosmically important not because they control the universe, but because they make it real in the only sense that ultimately matters. From this perspective, extinction is not just a biological event. It is a cosmological one. The disappearance of conscious observers reduces the universe's capacity to experience itself. Each lost observer is not merely a loss of life, but a loss of perspective, a reduction in the universe's self-knowledge. If all observers vanish, reality does not explode or collapse. It simply fades into uninterpreted existence. The holographic universe also challenges the idea of an absolute beginning. If reality is fundamentally informational, then the Big Bang may not have been the creation of everything, but a transition in how information was organized. The universe may have emerged not from nothing, but from a prior informational state that we cannot access because space and time themselves were not yet defined. In this sense, beginnings and endings lose their absolute meaning. The same may be true for individual lives. Birth and death may not mark the creation or destruction of information, but transitions in how information is structured and accessed. Consciousness may arise when certain conditions allow information to become self-referential, and it may dissolve when those conditions no longer hold. What remains afterward is not emptiness, but unexperienced information. This interpretation offers no simple comfort. It does not promise personal survival or cosmic purpose in the traditional sense. What it offers instead is a reframing of existence. Meaning is not something imposed on the universe from outside. It is something that arises naturally whenever information becomes aware of itself. In this view, meaning is fragile, temporary, and rare, but also profoundly real. The holographic universe leaves us with a final, unsettling realization. If reality depends on observation, then the universe is not a finished object, but an ongoing process. It is something that happens, not something that simply is. Each moment of awareness contributes to that process, however briefly. Each conscious experience is a small act of cosmic creation. We are not passengers in a pre-written universe. We are participants in a reality that exists because it is being experienced. The universe does not merely contain us. In a very real sense, it needs us just as we need it. When observation ends, reality does not shatter. It falls silent. And in that silence, the universe remains encoded and complete, waiting forever for someone or something to look again.